Good afternoon. So Rohit and I will be presenting to you a little bit of tuning of both the Impala and HBase database environments. They are quite beloved. Lots of our clients, lots of people out there utilize these infrastructures, and out of the box, they're a little simplistic in their configuration. We're going to show you how to take advantage of the hardware resources that you will have.
Hello friends, I'm Rohit Pathak. I'm part of the Insight group in Clairvoyant, and I work here as a senior Hadoop administrator. My roles are like, I'm an on-call engineer, I'm like a Hadoop infrastructure architect kind of senior role. And I also work with client engagements in terms of understanding the requirements, creating their best possible solutions, and also doing some fine-tunings with the services. So I work with Michael. I have over 10 plus years of experience and 3 plus years of experience in Hadoop overall.
And I'm Michael Arnold. I've been doing the Hadoop thing for about 9 years. In addition to having been a systems administrator for Unix and Linux platforms, I like to describe my experience with Hadoop as I remember back when CDH2 was first came out. So I've been doing this for a little while. I tend to deal with the infrastructure side of things and keeping the daemons and hardware working.
So today we are going to talk about some of our case studies where we have solved complex level problems for a few of our clients. And these are mostly about database engines, our Hadoop database engines, which is widely used right now with our clients. So we are only going to talk about Impala and HBase today. I'll explain you how we walked through and how we were able to achieve this milestone. So Impala, I'm not sure how many of you have worked on Impala in general, but Impala is like a pretty fast database engine where you'll be working on pretty complex analytics and other jobs. So Impala, for tuning Impala, we need to think in a different way than how we do a normal MapReduce and other applications. So for our client, we had okay, so this case study is about one of our clients who are having problems for more than 2 years, and they have been trying to break out a fix, and they were having problems with their coordinators, and they had raised multiple tickets, but they were unable to get proper support, and they had crashes with the Impala daemons, and when we came into picture, we started analyzing their cluster and started tuning with our best practices and analyzing the cluster, identifying the resources which are probably the culprit of the problems. So as I said, they had issues for a long time, and they did not have any trends that would mark that this is a consistent issue. It was coming once and it was coming again. The threads that were spiking basically was on one of the Impala daemon, and ultimately the daemon were crashing due to it. So there was the second problem that they had was Impala queries on Hue, which errored out with the results and timed out. Sorry, it's difficult for me to just match the slides because it's not presenting here. Okay, so this is widely the graph which is showing that one of the daemons had a thread spike of almost 11K, and then it dropped off. If one of the daemon gets, disconnected, probably your entire Impala query gets hung up, and you need to restart the Impala service as general. So this caused a lot of hiccups with their jobs and applications. So that restart impacted them. This is another graph where it's showing about the timeout queries and the problems that they're facing because of these outages. Now, taking a deep dive into the problem statement and analyzing the cluster, we found out, we found out from the demessage logs that there were problems with their host on OS level, on application level, and in different formats. So these were the three culprits initially which we found. The disk errors, which showed that the slowness in the disk, and they've had some errors with the disk, probably because of very heavy load of the queries that are running, or probably the host being used for multiple reasons. And then we had JVM crashes reported by Impala. So the Impala coordinators, or probably the Impala daemons, were having problems with the JVM, and we tuned it to solve those problems overall. The last one is the HDFS file count snowballing. This is, in general, if you have worked on Hadoop cluster, the small files problem. This creates a big blocker for your entire applications. So to reduce these small files, we kept a step-by-step approach. I'll explain that later in the further slides. So as the development grew, so we stretched these tuning exercises for 2 to 3 months, and you can see a graph where as the development increased, their workload started increasing, and these small files keep populating, and it almost reached 1.5 million in a matter of 2-3 months that we were actually working with them. Okay, so the first point on the disk errors. So when we were working on the identifying the problems as mentioned in the demessage logs and other things, we actually found out that there were disk errors with some of the master nodes, and that also had problems with name node, journal node, and Zookeeper using the same disks. So this reduced the speed of how you're writing inside, and probably the caching was not happening. So we had to split those disks to solve this problem, and divide them, probably move those individual directories on different drives to solve the network I/O problems. They had problems with the RAID 1 virtual disk for journal node, which I mentioned. Now, with the host, with the bad disk, we had to decommission one of the hosts if your host is having a problem in general. So sometimes it's not your disk, but in general, your entire host which is unable to write in the given fashion. So we had those maintenance. We had to do a series of activities to overall tune Impala in general. Now, how did we find out? Even after changing the RAID formats, and also when we moved to a different disk, we were doing some regular scans on the disks to monitor whether it's functioning as expected. The third problem was, as I mentioned earlier, it was the small files problem. Now, when you have too many small files, your I/O actually slows down for writing. So they had compression for Parquet file. They were using Parquet files in order to compress, and the files were just in KBs. So compressing a small file, it was creating those I/O contentions for them. So we moved to the compactions to dynamic partitions, to use dynamic partitions, and this helped a lot for us when the number of files got reduced from 29 to 1. So that was a major, big success for us when we changed this. It completely depends upon the approach, how you are using it. Just because these compression techniques are available, you can directly start using them because some Cloudera recommends these. Based on application and based on your usage, you can decide what you need to pick up. Now, the failed executor connections. Okay, I forgot one thing. When we had those failed executors, the thread graph which I showed you earlier, So that actually increased the number of, the problems with the threads was because the disk was unable to write, and the consequent failures with the connections actually was creating those problems. So too many small files trying to write, increasing the I/O contention, the number of threads were increased. So we had to reduce that. And once we changed this to dynamic partitions, we were able to achieve on those thread counts, at least on the disk level. So there are multiple things we did after this. So I'll just go ahead. Now, this client probably was having a very complex kind of environment where they are using the cluster on more than 80-90%. So to give the scalability, in terms of scalability, to actually allow all those applications to run successfully, we had some further tuning that we made on the cluster. Now, the executors wise, we needed, was it too fast? Sorry. Okay, yeah. So in Impala 2.9, and which is actually CDH 5.12, there was a new feature. So let me explain you how Impala works initially. So Impala has daemons which consist of the coordinators and the workers. So basically, coordinators distribute the fragments of Impala to those daemons to process, and then it coordinates back whether the query is completed. It gets the status of the job that is being run. So after Impala 2.9 and CDH 5.12, basically they found out that the coordinators do not need to be on all the daemons. Basically, coordinators involve a lot of network threads and connections. So after this version, you can separate the coordinators from the daemons, so that the daemons can just, I would say, coordinators and workers. So the Impala workers will actually process in a different way. The network contentions will never be seen on those daemons. So separating the coordinators basically will help you that these coordinators will be dedicated to just split the job, monitor them, and get back the results. So that we were able to achieve when we divided these coordinators and workers. So the strategy, how we did was, we've identified the utility servers. The utility servers are ones which do not have the master nodes or worker nodes. It just have like the Uzi and Hive, Metastore, and those things. So we identified those, and we put the coordinators there so that the workers can have more resources to execute. Because, okay, so this is the coordinator. I'm just talking about the coordinators first, and then we can talk about the workers. So, as I said, the coordinators involve a lot of networking, and they need to communicate with all workers, daemons, and also with the data nodes. So that networking and CPU overhead would be reduced on the workers if we separate them. Now, coordinators in general need more JVM than the workers, or the memory parameter. So we were able to actually scale more memory on the coordinators because that was on a utility. It's not dependent on any master services which would be blocking. So we were able to actually give more preference to the coordinators here. So once we give more memory, basically the coordinators were able to actually do some metadata caching. And now, how did we decide on how many coordinators should we have? Now, smaller the better. That's the basic formula. So based on the size of the cluster, number of threads, and how much is the workload of your entire Impala. Based on that, we were able to actually decide and come to a figure of 3, that 3 coordinators should be able to suffice. Let's say I have a 10 node or 12 node cluster. So the smaller the better. And sorry. So the cluster processes are mostly running on the masters, and that's not blocking us here. And so considering the daemons and DDL queries that we have, and the average resources that are available at various stages. So this was one of the biggest achievements, and probably it collaborated with the version that we had. And earlier, whoever is still on 5.12 or before that, I would suggest they should migrate or upgrade their clusters to use this version and these features. Now, moving ahead, apart from just tuning on the service side, probably Impala daemons, we switched to using HA proxy, basically the load balancing of the cluster. Now, Cloudera does not recommend HA proxy because it's a third-party tool, and they don't actually officially support all these tools. So we were able to use HA proxy for our client and distribute the coordinators to actually get actual balancing out of it. This was another breakthrough where we were actually, so these HA proxy has like different settings and configurations which would decide which coordinator should come first and how should we distribute the workload. So I'm going to talk about, the first one is least connection. Now, depending upon, if you have the sessions coordinator with the very less number of connections, then you can go with least con for HA proxy so that it would actually balance the load evenly. And this depends upon the number of connections that are actually established from the load balancer to the Impala daemons. Now, the round robin, as the word says, it distributes connections to all the coordinator nodes, and it distributes in a random fashion, whichever is the next one. But consider that if your one daemon is pretty slow and you still keep on increasing the request for it, in that way, this fashion, you'll get actually overloaded with one of the daemons. So depending upon your workload, again, you need to decide the best possible algorithm from the HA proxy. Stable balancing and benchmarking. So we did, when we ran through all these, we actually did a lot of performance testing, workload, increasing the workloads, balancing, identifying which daemons were actually getting more load and how we were able to solve that problem. The third one is source persistence. Now, this is required because we were having problems with U connections. So how Impala connects is one is through Impala shell. The second one is through your Hue database editors. So when we're having problems with Hue database, basically the settings were actually not allowing us to have sessions for longer period, and the logs were not getting removed. So in some way, we had to test these as well. So this source persistence will actually help us with fixing the problem with Hue connections. So 21050 port is for ODBC connections, and 21000 is for our normal U connection. Sorry, the other way. 21050 is for the U connections. So this source persistence were actually, what it does is, so it will decide which server will request, get the request first. And if you know about the sessions, we have sticky sessions when we establish connections from U to any database or probably Impala. So this setting probably was helpful for us. And now there are 9 parameters apart from just selecting the algorithm which we were able to fix. One of which is the timeouts. Now, if I just want to brief about why timeouts are important here is when there are settings when you run your Impala queries. So on Impala level, you'll set a timeout, but that gets connected to a load balancer, and the load balancer will have its own timeouts. So you will not able to understand why your query is being stuck at some point. Even on the background, if it's completed, but your timeout was very small than what the HA proxy or any load balancer had its timeout. So that load balancer will timeout after a particular time of a greater value. So might be your query was completed, but Impala itself declared that this was failed and it will put a retry and all such combinations. So we were able to fine tune this using the load balancers. So these are our 4 things which we are able to help our clients with Impala. I'll hand over to Michael for our achievements on HBase tuning for another case study.
All right, so we'll be going over a case study of a client dealing with an HBase environment. And give me one moment, let me see if I can get this thing to show up. Oh, I can't. So, we had a customer. They had an existing HBase setup. It was unmanaged, straight Apache HBase, running on OpenBSD of all operating systems. They were running OpenTSDB application on top of this, which is a lot of time series data of just monitoring values from various devices in their environment. They wanted to, of course, upgrade their HBase version and then come under the Cloudera managed environment that we had set up for the rest of the other clusters there at that customer. They wanted newer hardware, make sure they got plenty of RAM for the HBase environment that they were going to be building. And of course, SSDs. I mean, what could go wrong with putting a bunch of fast storage into a machine? Luckily, that did not have any impact on the performance tuning we were doing for them. So out of that environment, we did have a few things that we were looking for, and well, really there weren't any gotchas because the environment wasn't built yet. We just knew that we needed to tune HBase to use more than the default amount of memory you might otherwise get out of Cloudera Manager configuration. So first thing was to make sure that we were using JDK version 8. I think they were still using JDK 7 in their existing OpenBSD environment. And the first thing we were looking at was you're going to need to go JDK 8 because of a lot of the features and functionality that will be available in it. First thing we looked at tuning was collecting the information on garbage collection. By default, there's no logging of any of the GC events going on in the region server. So we went into Cloudera Manager, went to the safety valve, and started adding all of the tunings so that we could print out every time a garbage collection event happened and put it into a log file. There are a lot of configurations basically to put the date timestamp in there, what happened, various policies that are going on, and the flags that are happening for that particular garbage collection event. Next, we went and turned on log rotation of that GC log, because if you were to go and restart the region server, it would basically overwrite that log. So we wanted to make sure we had a different unique log name every time it started. And instead of it filling up the disk, we would make sure that it could rotate. So we'd have, once the log hit 200 meg, it rotates. We only save 10 of them so we don't end up filling up the local disk. Next, the important part. We knew we were going to use more than 16 gig of heap. In fact, we were going up into 100 gig because these machines had tons of available memory. In order to deal with the amount of data that goes into a heap of that size, we needed to use the garbage-first garbage collector. This will allow us to make sure that instead of waiting until there's memory pressure in the heap, garbage collection happens within a certain time frame, and that time frame we have here is 100 milliseconds. So every 100 milliseconds, garbage collection happens. And it happens so often that it doesn't have an impact on performance. It's very small. You just get tiny little hits instead of going along with very minimal impact, and then all of a sudden, poof, you've got a stop the world garbage collection that happens on your region server, which in an HBase environment with low latency means you've just burnt out your SLA. Next, we needed to tune that G1GC configuration. So we went in and set the parallelization of the reference processors. We removed the resize plab. And then we set how many parallel GC threads that we wanted to go on that machine. And we've got a little bit of math here that says the number of logical processors on that machine, say there's 16 CPUs. We're going to come out with basically a mathematical formula to figure out how many of those we want to use for garbage collection. We want to unlock some of the experimental VM options, and then we want to set our G1 new size percent to 3. Now this is based upon how much memory you're going to use. The details of that are in the link that we've got. So where do these settings go? We've got the path here for Cloud Manager configuration. You can go into the CM UI and go and find the advanced configuration options for the region server. There are not any button presses or fields to fill out. It's just a text area where you cut and paste all the values. Similar for Embari, we've got the path to the basically text box where you would plug in your XML for these configurations. Now, in addition to the GC tunings, we've got the heap size of the region server. Even though we've got tons of RAM on the machine, we only want to do heap sizes up to a certain point. Once you get past 31 gig, that's when you start running into interesting things. So we wanted we wanted to use most of the memory, but there were other methods enable us to do so. So the main heap of the region server, we wanted setting to 31 gig. And I'll go into that precise reason why here shortly. Did I just skip one? Aha. And that reason, not to set the value between 32 and 48 gig, is there's this functionality inside the JVM called compressed OOPs, ordinary object pointers. And it's the way the JVM stores pointers to portions of memory. Up until just before 32 gig, there was no need to have, the fully uncompressed value of this. So there was a method that they developed to compress the namespace that you could use to store all these pointers. But once you got to 32 gigabytes of memory, you had to uncompress them and use the full value for that namespace, so basically 64-bit pointers. And now all of a sudden, the amount of objects that you can store in memory that you can reference gets cut in half. So you actually lose the ability to store the same amount of objects at 32 gig than you had at 31 gig, or just before 32 gig. So the recommendation is don't do values of heap between these 2 points. Stop at 31 gig or go to 49 gig. Now, in order to use more memory, because we were looking to tune at 31 gig, there's this concept of the off-heap cache, or the bucket cache. And this is an advanced configuration. There's no tunables inside Cloud Manager or Embari. You need to understand the concepts behind all of this. If you do enable the bucket cache, the on-heap cache is then used for the Bloom filters and indexes, and the off-heap bucket cache is used for storing and caching the actual data blocks. And the off-heap cache is not subject to the garbage collection. So you're only garbage collecting 31 gig of your primary heap, and then you can deal with allocations of this off-heap cache in a different manner. Now this is what's referred to as the combined bucket block cache configuration. And it allows you to use, as I said, both of the garbage collection in your main heap as well as allowing HBase to manage the bucket cache memory allocations and garbage collection there. Wait a minute. All right. So Also, in addition to the configurations, you need to also set the advanced configuration for the client environment. This is another set of variables. So in addition, you set the heap size, but you also have to set a variable for the environment to be able to take advantage of that. So there's the HBase off heap size. You set that to the value of basically the value of your heap. And you also set the HBase options to give the Java flag of that same value. In addition to tuning the block cache, we also decided we were going to increase the number of write-ahead logs and enable parallelization of those. So we basically decided what's the number of hard drives in the machine. We're going to divide that by 3. So these machines had 12 disks. We decided we're going to set the number of write-ahead logs to 4. That way we can take advantage of those extra disks in there and provide the ability to get more I/O out of the process. This then takes advantage of the underlying HDFS parallelization, and you get basically increased throughput. In addition to the tuning, we turned on Hedged Reads for HDFS. This basically allows us to tune the amount of time we're willing to wait for a DFS client to fetch a block off of disk. If that block has not been retrieved in a specific amount of time, we'll start up a second fetch from a different data node. Whichever one comes in first, we win. Maybe the first one was blocked for whatever reason, the node crashed and went down, so we'll just start up another one and hopefully get that response back sooner. You can set the threshold in milliseconds. This example here is showing 500 milliseconds. If we don't have a response back, we'll spin up another request. References. So all the stuff we've got here, I know seems like black magic at times. We've got some references as to information where you can read up more on all of this. One thing that I will recommend is the last link here to gceasy.io. Once you do get those garbage collection logs, this website provides the ability to analyze and make graphs that'll show you how often your garbage collection happens and how it's impacting your performance. Any questions?
Yes, please.
Sir? Oh, there we go.
So what is the recommendation for the drives? Like for HBase, it should be SSDs or it should not be SSDs?
So in general, my recommendation for HBase or pretty much any Hadoop environment is not SSDs, it's just magnetic disks. There are times in certain situations where they will give you an advantage. But in the case of OpenTSDB, we saw no real performance improvement. It was just a way of hedging our bets. And for our use case, the client had decided already that they were buying SSDs, so we said, okay.
And what about write-ahead? Like you said that you had 12 disks, and how do you come up with the formula of 12 by 3, basically?
Was this for the write-ahead logs or?
Number of write-ahead logs. I think.
I'm sorry?
Number of write-ahead logs.
I believe there was a formula in the link that we had on that slide, which I'm not recalling at the moment, but that goes into great detail as to why to choose that particular number.
So in HBase, we have something called as compactions. So would you be able to share your experience on how do you strategize the major and the minor compactions to deal with performance?
So in general for HBase, our recommendation most of the time is turn off major compactions. You don't want the system automatically performing those on your cluster. You want to be able to schedule it at a time when you control. HBase doesn't know when the low volume time of your application is, when's a good time to do that. It simply says, it's been 24 hours, let's kick that off. maybe that's in prime time for your application. So we always say, turn that off and instead schedule the major compactions. The minor compactions tend to be very not so invasive and need to happen, so we let those go as needed. All right, well, thank you very much.